For this lab, an object will be analyzed in a free fall. The objective is to observe the net force on the object as it falls, so that a computational model can be formed based on the forces of gravity and the drag forces on the object. Also, the computational model and the experimental data will be compared to see how well the computational model recreates the experimental data based on Newton's second law of motion. This is a video of a crumpled up bag of Doritos falling from rest. The position of the object over time is shown here. Based on Newton's second law, if the velocity is not constant, then there must be a net force acting on the object to prevent this from happening. In a free fall environment without drag, one would expect the change in velocity to always be a non-zero value. In order to find the net force on the bag, the component forces must be considered. The weight or force of gravity on the object and the drag force on an object are the two forces that make up the net force in this lab. As seen, we can consider a drag force that is proportional to the velocity, or a turbulent drag force that is proportional to the velocity squared. We will look at both to see the differences. Before the VPython code can be run successfully, the initial conditions must be inputted correctly as seen here. Please pause the video and look over the code carefully if you are interested in all the technicalities. Now, we will first look at the object that is falling that would hypothetically not experience any drag forces. In order to do this, both the proportionality constants for drag and turbulent drag are set to 0. For each test case, however, the loop will remain unchanged and will implement Newton's second law, as seen here, to change the position and velocity of the ball over time. Also, the loop is set for a total of 0.6 seconds, which is congruent to the amount of time the ball fell in the video seen at the beginning. The force of gravity on the ball is represented by the yellow arrow, and as you can see, the force is constant throughout the time the ball falls. Take a mental image of what this model looks like so that you can compare it to the model that will be looked at later on. For the next model, the drag force that is proportional to the velocity is observed. The proportionality constant was found by trial and error while running the code to get approximately the same final position for the experimental data and the model. This constant is now used in the code, and all the rest of the code remains unchanged. As you can see, the object is now experiencing a drag force upward, which is represented by the blue arrow. The magnitude of the drag force changes over time and is not constant. Mentally compare this model to the previous, and once again take a mental picture of what this model looks like to compare it to the final model. When the models created are compared to the experimental data, it is easy to see that the experimental data appears to follow the path of the drag force model more accurately, but there are still some deviations during the middle of the free fall. We will now look at the turbulent force that is proportional to the velocity squared to see if we can improve this model. The proportionality constant for the turbulent forces was found in the same manner as described for the drag force and is inputted as shown. The computational model seen here shows a much larger final drag force magnitude than seen earlier, and it also changes as time goes by. This is the turbulent drag force. Here is the comparison of the new computational model based on the turbulent drag force to the model without drag forces in the experimental data collected. The turbulent drag force model more accurately depicts the motion of the experimental data than the drag force. And if you are skeptical, please go back and look at the other graph seen earlier. As you can see, the experimental data is very well depicted by the computational model based on the principles of Newton's second law. What does it mean? We will examine the velocity versus time predicted by our models with and without drag and determine which models predict a terminal velocity. When the turbulent drag force and the non-drag force models are compared, the terminal velocity is predicted by the turbulent drag force model. The model without drag shows a constant change in velocity, which is represented by the perfectly straight green line. The model with the turbulent drag forces predicts that the object will eventually reach a terminal velocity and the net force on the object will eventually be 0. What if? Imagine that the object was initially thrown downward. Will the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? I chose to hypothetically throw the ball downward with a speed of 3 meters per second and then modeled the two scenarios as seen in this chart. If you were to extend the chart or take the limit of these functions as the time approaches to infinity, the bag would have reached a final terminal velocity that is equal for both instances. If we were to simply analyze the ball drop from rest only from a time period beyond which the ball has reached a velocity of 3 meters per second downward, then the graph would look identical to the blue line shown here. Therefore, the terminal velocity would be the same at both graphs. Throughout the lab, we have seen that our computational model that includes a net force based on the gravitational and turbulent drag forces experienced by the bag accurately depicts the motion of the experimental data based on Newton's second law of motion. Thank you for watching.